So we've talked about rational expressions. We've done a lot with rational expressions. What I'd like to do now is talk about these as functions. And we've already done this a little bit because we've talked about domain and range. So let's start with the most basic reciprocal function. The most basic one is just y equals 1 over x. And we call it reciprocal because our x is in our denominator. Okay, it would be, so f of x is equal to 1 over x. This is the reciprocal of f equals x. So that's just an explanation of the name and where it comes from. So in our reciprocal functions, we have an algebraic expression in the denominator, and we're left with an x. So even after we do any sort of simplification, we have this x in the denominator. A lot about reducing rational expressions. So here we're saying even after we reduce, we still have this x in the denominator. So let's take a look at what some of these reciprocal functions look like. So this is 1 over x. This is what y equals 1 over x looks like. And I'm just writing this in the board notes as well. So you can see here that these reciprocal functions have a minimum of 2 pieces to their graph. Let's look at it in a little bit more detail. They have 2 pieces to their graph, okay? And if you notice here, we're approaching this line, this y-axis, we're approaching it, but actually if we take a look, we never actually reach this. It's the same as it is with exponential. Okay, so we approach this line, but we never reach it. And the same thing is true for the x-axis. In both cases, we're approaching the x-axis, but we're never reaching it in both sections of this graph. And this would be y equals 1 over x. Let's take a look at y equals 1 over x squared, because that's another example. That's another example of a reciprocal function. So this one you can see is a little bit different. Y equals 1 over x squared. We have 2 sections to our graph. Now we approach the y-axis and never reach it. We approach the x-axis and never reach it. But here we're in quadrants 1 and 2, okay, instead of quadrants 1 and 3. So I don't know if we've ever mentioned quadrants before, but we're talking about the quarters of the graph. So this part is quadrant 1. Then if we go over here, that's quadrant 2. If we go down to the bottom over here, that's quadrant 3. And then down here is quadrant 4, because our coordinate plane is divided into 4 pieces. So we call each piece a quadrant. So here, we're above the x-axis in both cases, but we still have this x and this y-axis that we're approaching but never touching. So we have names for those types of lines. Again, I'm just going to put this into our board notes. And this is true of our, when we raise it to an even power and when we raise it to an odd power. Okay, so we approach the y-axis. We never touch it. We approach the x-axis, We never touch it. And this actually makes it easy. We could see what our domain and our range is in both of these cases. So in this case, I'm going to put this in standard or set notation. So in this case, for our domain, it's all real numbers, right? We go all the way to negative infinity, all the way to positive infinity, but we don't have x equals 0. So x is not equal to 0. And that's easy to see from this function. Okay, we talked about this when we were talking about rational expressions, what the domain is. And we could see that if x is equal to 0, then this would be undefined. Okay, so at x equals 0, which is the y-axis, it's undefined. And then actually the range here is the same except for y. So y can't be 0 here either. Okay, there is no way that we could get a y value that's equal to 0, because the only way that we could get a fraction that's equal to 0 is if the numerator is 0 and the numerator is 1. Okay, so let's just write that the numerator isn't 0. This is the only way. Fraction equal to 0. So we're saying that can't happen. So because it can't happen, y can't be 0. And then over here, the domain and the range is similar. The domain is actually exactly the same, right? We go from negative infinity to positive infinity. We don't have 0, because if we had 0, that would make it undefined. And the difference here is that for the y value has to be positive. And why does it have to be positive? Because we're squaring our x here. So if x were negative, in 1 over x, we would get a negative number. So we would have y values that are negative. But here, if x were negative, then the x squared makes it positive. So we're only going to get positive numbers as our answer here, which means that our range is that y is greater than 0. So it's not equal to 0 because, again, this is a 1. There's no way that the fraction equals 0, but it has to be greater than 0 because we're always going to get a positive number. Okay, so this is the domain and the range, and we're going to look more at domain than we will at range of these functions. Okay, so in order to look at domain, there's something that we need to define first. So we talked about this a second ago, that we have this line that our graph approaches, but it never quite touches. I'm not sure if we mentioned this before, but this is called an asymptote, so it has a special name. Okay, it's a line that any curve approaches but does not touch. Okay, so it can be a curve that's approaching it. You're not going to get another line approaching it because that wouldn't make sense. Lines cross or they're parallel, so they're never going to approach and not touch each other. So the asymptote is the actual line. Okay, so let's write that down as well. And I'm just going to add in here, again, just for the purpose of the board notes, I'm going to add in here that y is always positive. Because x squared is always positive. And it's not really the denominator that we're looking at. What we're really saying is, sorry about that, what we're really saying here is that x squared is positive, the 1 is positive too, right? We already have the 1 in there, so we don't have to worry about the numerator because the numerator is constant. Okay, so let's define asymptote because that's going to be a big part of looking at domains. So an asymptote is a line that a curve approaches but never touches. And if we have an asymptote, it's not going to be in, if it's a vertical asymptote, it's not going to be in the domain. If it's a horizontal asymptote, it's not going to be in the range of the function. And we'll talk about that we could write that in there actually here. So a vertical asymptote is not in the domain of the function. That's because it's an x equals. That's why we say it's not in the domain. It's a vertical line. And a horizontal asymptote is not in the range of the function. That's what we're really going to be talking about today is asymptotes. Okay, so let's go back to something that we've already done. Let's say that we have f of x is equal to 1 minus x over x squared minus 7x plus 12. Okay, now for right now, all we're going to do is we're going to talk about vertical asymptotes, okay, and what's happening in these graphs with these different vertical asymptotes. So in order to find a vertical asymptote, we're talking about the fact that it's not in the domain of the function. So let's find the domain. So if you remember, in order to find the domain, we have to factor the denominator because we're talking about where is the denominator equal to 0. In the domain of the function, the denominator can't be 0. Okay. If you remember, we said if x is in the domain, then the corresponding y has to be real and it has to be defined. So here we're not going to worry about real because we have no radicals. Okay. A reciprocal function has no radicals. So we only have to worry about the denominator being 0. So if we simplify, not really simplify, but factor, in the denominator, we get x minus 4 times x minus 3. Okay, so our domain is that x can't be 4 and x can't be 3. Now here's what that means. Let's go take a look at this function. That's this function right here. Let's close. Now what that means is that at x equals 3, we have a vertical asymptote. And we have another vertical asymptote at x equals 4 because that's where our denominator is equal to 0. Okay, so vertical asymptotes and we're going to add a caveat to this, an exception. Okay, the exception is, and we'll go through an example of this, is unless that factor cancels. So if x minus 4 canceled, then we would have something called a hole, okay? And we'll show you what that looks like. If we have a factor that cancels, then we have a hole in the graph. So, for example, let's say that we have f of x is equal to x minus 6 over x squared minus 36. Now we want to find the domain, so if we find the domain doesn't change, okay? The fact, if we do this, we factor, okay? So if we factor, we get x minus 6 in the numerator, nothing to factor there. And then this is a difference of squares, so we have x plus 6 times x minus 6. Okay, so our domain is still that x can't be 6 and x can't be negative 6. Okay, if you remember, we said when we were talking about domains with rational functions, we said do it before you cancel anything. Okay, so we would cancel x minus 6, we still get an x plus 6 in the denominator. Right? We cancel this out, and I'll write it here. We get 1 over x plus 6, and that's true, but there's one difference, and the difference is that in 1 over x plus 6, it's okay if x is equal to 6. But in x minus 6 over x squared minus 36, it's not. So the domain is different, okay? So these are equal, but the domains are different. What we're saying is that in the second one, 1 over x plus 6, x could be 6. But that's not true here. X can't be 6 in this function. So the domain of this function, notice this is a case where it's much easier to write it in set notation versus interval notation. But you're welcome to do it in either way. In this case, both of these are true. Okay, so you can't have either one of these. So let's take a look at that graph. That's this one here. Okay, so you could see here, you could see the vertical asymptote at x equals negative 6, right? And if you go here, this tells us that there's a vertical asymptote at x equals negative 6. It doesn't cancel, okay? So vertical asymptotes exist when our denominator is equal to 0. At negative 6, our denominator is equal to 0. But our denominator is also equal to 0 at 6, but you could see there's no asymptote here. And you can't really see it in this graph, but you can see it if we actually go to the point. What you get here if we go over to 6, you can see that the y value is undefined. It's a little hard to see here, but you'll see an open circle. There's an open circle on the graph at x equals 6, okay? So instead of having an asymptote, what we really have in the graph is a hole. So if the factor cancels, we have a hole in the graph, okay? We just have an open dot. So we could see what's going on in the graph. So here, typically you would draw it with a hole, okay? So here, for some reason, Desmos doesn't do that, I guess because it's such a tiny, tiny, tiny point that it's not going to show it to you. But you can see when you do this, that it will say at x equals 6, it will tell you it's undefined. And if you go directly to that point, you can sort of see it here. There is a hole in the graph. Okay, so what that means is that we could find all of the vertical asymptotes and all of the holes. So here, at x equals -6, we have a vertical asymptote. And at x equals 6, we have a hole. So, and that doesn't always happen. It's only if we have a factor that cancels. If we have a factor that cancels when we reduce, then we have a hole. If it doesn't cancel, if nothing cancels, then we only have asymptotes. Okay, let's take a look at another one. And all we're going to do is we're going to find the vertical asymptotes and the holes. So by doing that, we're also finding the domain, but we're just identifying this. So let's take a new function. So if we do this, we have x over x squared minus 25. Okay. If we try and reduce this, we have to factor. We have x plus 5 times x minus 5. So where does the denominator equal 0? At x equals -5 and at x equals 5. Okay, this x equals -5 comes from x plus 5 equals 0. And this x equals 5 comes from x minus 5 equals 0. Now, in both of these cases, we have vertical asymptotes. Because nothing cancels. Okay, if something had canceled, then we would have had a hole, but nothing canceled here, so we didn't have to worry about that. Okay, let's take another example. I'm trying to find, let's take y squared minus 5y minus 6, or we'll do x squared, sorry. Equals x squared minus 5x minus 6 over x squared minus 1. So in order to find vertical asymptotes and holes, that's what we're looking for. order to do this, we're going to factor. So x squared minus 5x minus 6 factors to x minus 6 times x plus 1. And an x squared minus 1 factors to x plus 1 times x minus 1. So you want to factor first. Okay. If something cancels, then what that means is that it's a whole. So here, this x plus 1 cancels. So x plus 1 has a whole. Okay, we have a whole at x equals -1. Now x minus 1 doesn't cancel. So we have a vertical asymptote. At x equals 1. So this is how we develop, this is how we find wholes and vertical asymptotes. We're trying to figure out where the denominator is 0.